At the moment, there is no tutorial planned for today. I'll see, we may have one on Thursday. The real issue, I thought they should have a tutorial on this. Explaining to you precession, but I said it to them, you didn't know. And it's really not that difficult, I just didn't have the time. Okay, that's all. Okay. We're talking about black holes.
Einstein equation without the cosmological constant.
Correct.
And could we modify it to?
Yes, the cosmological constant, as you'll see, is not relevant in these scales. It's too small. Actually, it's supposed to have the cosmological constant, as its name suggests, affects cosmology, which is large distances. Here we're talking about small scales.
But can we modify it analytically, or just saying negligible?
You can, but again, I'm not sure what you mean by analytically.
Do we have a function that is exactly the Schwarzschild solution with when the cosmological constant is exactly zero, but nothing, almost, כאילו אין משהו תיקון מעבר לתורת ההפרעות, משהו בסגנון הזה של שעת איינשטיין?
לא שאני מכיר. Okay. If somebody found some solution, that's, I don't know about. But anyway, it's not relevant. What I mean by not relevant, okay. I go back to the thing I keep on telling you, right? At the end of the day, we're talking physics. And when we talk physics, it means that everything has to be measured and give you some predictions. And as you saw in your homework, which you're supposed to see, if there are corrections which cannot be measured, right, then it's physically meaningless to talk about it, unless you can find a way of measuring that, unless you have some theory. At the moment, we do not have anything that tells us that Einstein is wrong, that we need a different solution. Modulo, life is more complex. I mean, Schwarzschild solution is the simplest solution that we have. There are more complicated solutions. In particular, there is a rotating solution, the Kerr solution. There is also a charged black hole solution. It's called Reissner-Nordström solution. This we don't expect to see in nature, this solution, because the black hole can be formed charged, but then it will discharge immediately, basically. So we don't expect to see that. Rotating black holes we do expect to see, and we do see them actually. Okay? We do not know of any object that does not obey them at the moment. Maybe there is, we don't know.
Discharge is emit the charge or absorb the opposite charge?
I think it will be absorbed opposite charge. Right? What do you mean charge, right? I mean, black holes are formed of matter, of particles, right? Particles, right? We know, as far as we know, that nature is neutral. We have charged particle and the same amount of particles that are charged with a plus sign and are charged with a minus sign. We don't have any evidence that things are not. So if a black hole is formed, you can form a black hole where it will be, just protons fall in, let's say, and there will be an electron cloud. But then you'll form a potential, and then this electron will just get it. Okay. So what did we do? So we looked at the Schwarzschild solution. We looked at the null light ray propagating in the radial direction. So null radial direction. And we find out that ds squared is 0, so null is a minus 1 minus 2 gm over r dt squared plus 1 minus 2 gm over r minus 1 er squared. And then we said dt over dr is plus minus 1 minus 2 gm over r Then we just plotted that. This is R, and this is T. This is R equal to 2gm over c squared. And we saw this interesting phenomenon that happens. Again, we're talking about null-radial geodesic. Right. When we're very far from this special radius, then the t over the r approaches plus minus 1. So if I plot the light cone, it will look plus minus 1, 45 degrees. But as we're approaching this t over r, the special radius, then the light cone shrinks. Which means something very strange, right? If we're trying to get into the black hole, we send a light into the black hole, it will get closer, but as it gets closer, it gets slower and slower and slower. So as an observer, which we're sitting somewhere here in our spaceship, right, we will never see any object that crosses this Schwarzschild radius. It's going to take infinite amount of time for us to see that. Doesn't mean it's not going to happen, just we could never be able to see that. What was the question?
Yes.
Yes.
The observer, if he tries to measure the speed of the light ray, does he measure something smaller than c?
No. Light ray is always c. But
Yeah.
the question is how you measure it, right? You measure it here. Let's say there is another object. Let's say there is an astronaut that tries to get into the black hole. Right? So I have another astronaut that now goes into the black hole. Right. What do I see? I don't see the astronaut. I see the astronaut sends me signal. Right? The astronaut sends me a light ray. Okay. So I see the light ray. This is the message that I'm seeing. When the light ray comes to me, it's always traveling at the speed of light. Right? What I'm going to see is that the signals are going to be slower and slower. You get less and less photons, and they will become redder and redder according to gravitational redshift as it approaches. So I'll see that getting closer, but it's going to take much longer time for the signal to arrive to me. Yeah.
The light cone, the normal light cone that we mentioned,
Yeah.
these two are the opposite, meaning like
Plus minus 1.
yes, and this means a light ray that goes inward and a light ray that goes outward.
Exactly.
As for the cones near,
Close, yeah.
it's not. It's just
They also go inward and outward.
yeah. But it's not forever like that. I mean, the cone goes something like that because as the light moves away, the angle changes. So if you complete the cone as I mean,
you mean yes, it will go.
if you make it longer, then it
I
doesn't
mean,
stay a
the
cone,
idea,
right?
if I take a light ray, starts from here, right? It will
Yeah.
go along this direction, and you're right, it will sort of
Yeah.
open up like that.
Until one.
It will reach the one eventually.
Yeah. And what happens to the other thing?
Well, it could get slower, but it will get the opposite, right? It will get, it will never reach the. But as we get closer and closer, the t over the r gets closer to.
Oh.
Okay, so it will look something like that.
It's all tangent to the event horizon.
That and that will be that. I don't know, whatever.
But if
Use your
it's
imagination.
Tangent to event horizon, or just stopping at the event horizon.
What?
There's
It's
no.
never gonna stop. It's never gonna stop. It's just never go. We're never gonna see in this coordinate system. We're never gonna see anything that crosses it. It's never gonna happen. It's gonna take infinite amount of time. Then we said, look, this is sort of an artifact. It's an artifact because we chose to express the space-time in this coordinate system t, r, theta, and phi. If we were to choose to express the space-time in other coordinate system, which we can at the end of the day, right? This is a Schwarzschild solution. I can write it down in different coordinates. I may have different results. Yes.
במערכת צירים הזאת, אנחנו רואים שהביטוי ל-dr הוא ביטוי שפרופורציונלי ל-1 חלקי r פחות r שוורצ'יט. אין עוד איזה קרוב.
1 פחות r שוורצ'יט חלקי r.
אם אני חושב ש-dt שדלתה r כאילו בדיוק שווה ל-r שוורצ'יט, אני אקבל משהו מתבדר.
כן.
אם יכול להיות מקרים אחרים. אם נגיד אבל החזקה הזאת הייתה מינוס חצי, אז האינטגרל זה היה כבר סופי. אנחנו רואים דברים כאלה?
מה זה רואים? מתמטית, ולפתור את זה במחשב, ודאי שאתה יכול לראות את זה.
יש סיטואציות שאנחנו פותרים מתמטית ורואים את זה.
זה כבר, אתה יודע, זה beyond Einstein theories. כי... שוב, תזכור. כל הרעיון זה פתרון של משוואת איינשטיין. We're solving Einstein's equation. And we get Schwarz's solution. If there is another solution, we didn't find other solution to Einstein's equation. Now you can find, a different solution, maybe. Explore it, find a different solution, and then you can explore what this new solution means. If you find another solution, you'll be quite a hero. In fact, you cannot do that. I know you cannot do that because there is a mathematical theorem that states that the Schwarz's solution is unique. And I didn't give you the full proof, but I mentioned it to you. Okay? A unique vacuum solution, steady state, non-rotating. So anything else would be, you have to add up some other types of things here. Okay. So I said, okay, we have something strange. So let's try to play with the coordinates. Why do we have to use T and R? Maybe we can use different types of coordinates. And then we introduce new coordinates, the 2 to R coordinates. R star is R plus 2gm ln of R over 2gm minus 1. And then we introduced yet another coordinates, u tilde, which is t plus r star, v tilde, which is t minus r star. And then we said rather than t, let's use u tilde. And when we do that, we wrote down the non-geodesic, radial non-geodesic, as ds squared is minus 1 minus 2 gm over r, du tilde squared plus du tilde dr plus dr du tilde plus r squared d omega squared. Okay, so the coordinates u tilde r, theta, and phi has a name. These are called Eddington-Finkelstein coordinates. And then when you do the same calculation, you find out that du tilde over dr is 0 for the infalling, and 2, 1 minus 2 gm over r minus 1 for the outgoing. When we make the same plot, but now it's u tilde, gm over c squared. We find something quite interesting. We find that when we are very far away from this special radius, ingoing we can always go, and outgoing we can always go. Get something like that. That's our light. But as we are approaching this special radius, incoming we can always do, but once we cross it, the outgoing becomes infinity. And when we're inside, it actually becomes negative, so the light going would look something like that. So, we achieve two things. First, we suspected that not being able to cross this radius is really an artifact of the coordinates. Right? So if we're using different coordinates, there is no problem. We can cross this radius. And indeed, we said physically, that's what happened. I mean, if there is somebody who wants to dive into a black hole, he can do that and reach there within a finite proper time of himself. We, as an observer from the outside, will never see that happens. But for this guy, there's no problem. From his clock, 5 minutes and he's there. But there is something very strange happens here. Once you cross, that's it. All future directions take you into smaller radius. So once you're inside, you can't even stay at the same radius. You have to fall in to the singularity at r equal to 0. And there where we say, laws of physics stop being valid. In fact, you're going to die even before that, because the tidal forces, namely the force that you're going to feel on your feet, is going to be much stronger than the force you're going to feel on your hands. It will be just torn apart. So it's not a good idea to do that. But in principle, you can do that. But the point is that this is really a boundary of the universe, because once you cross, things could happen right here. But we've got no way of knowing, because there's nothing that would tell us, poor guys, let's say, or lucky guys, let's say, outside, there is nothing that would tell us what happened here. So that's why this is called event horizon, because all events happen inside are obscured. Obscured from our view. Yeah.
You said that all future directions go inside. And
yes.
How do we know where is future? I mean, you just change the time. U is not the time.
Yeah, U is a time-like coordinate. Yeah, it's a time. Okay. It is a time in a sense. You can go back to the time, but it will be ill-defined here. Okay. But essentially, because we have this minus sign here, this is act as a time-like coordinate.
But the horizontal line is not a present.
Horizontal line is fixed U, right?
Yeah.
This is U constant. So I'm just freezing in the picture.
This is not a present. I mean,
this is a present. This is a present. I mean, this is, when I draw it like that, that means this is now. This is what happens now. I'm somewhere on this line here.
But an incoming light ray is all over the present. It's all over.
I can put it wherever I want.
No. If I start from the center of the cone here, the center of the cone,
yeah,
and I move inside, then the trajectory of the light ray is directly into 0, right?
Yes, but this is because it's the combination of T and R here.
Okay. But the future is future here.
Future
going
is future,
upward
yeah.
is
going upward is the future, yes.
Okay.
Increasing U tilde. Increasing U tilde is equivalent to increasing time.
And also, if I go into the black hole, I would be torn apart. But what about an electron that goes in? It will need to be torn apart into what?
I don't know.
Okay, we don't know.
I don't know. Electron is a basic part. Again, as I said, we understand physics up to a level, up to a limit. Once the densities become so high, and we know exactly when is this limit, right? It's the Planck mass, the Planck scale. Once we reach that scale, or Planck energy, it doesn't matter, it's the same thing. Once we reach this scale, it's something like 10 to the 19 GeV, so 10 to the 28 electron volt. Then we don't know what happened. That's what people do in CERN, try to reach higher and higher energies. They will not reach that Planck scale, there's no way. But we reach higher and higher energies and we can get a better understanding what happened at higher energy.
But just to be sure that we don't have a theory about ripping the electron apart. I mean, we can imagine that I would be ripped apart because...
Yeah, no, I understand what you mean. No, electron is part of the standard model. There are elementary particles, electrons, elementary particles. In principle, yeah, that's another thing, right? We don't quantize anything. Right? There's no. If you really want to quantize, you have to quantize space and time, which is likely going to happen inside. But again, it's not going to be the same quantization that you're used to from quantum mechanics. You have to quantize the field. Okay. But let's stick with classical physics. It's still interesting enough, I would say, right? Without getting into the quantization. Do you think something strange here, apart from the whole story of life? Once you cross the horizon. Is there something which you feel is that I treated you, I cheated you in a way?
After we cross the horizon?
No. In the derivative I did. I mean, the calculation, mathematically the calculation is correct. I did not. It's been checked by myself many times. But of course not just by myself. Mathematically it's correct, but something in the physics here. Don't you see there is something which is a little bit like it was a little bit of cheating here. No, that just means that I just want to move to coordinates where I can see what happens inside. That's all the cheating.
We have a missing point in the center. We don't.
No, that we knew already that the curvature goes to infinity. Yeah.
Did you find a new time?
No, it's okay. Just play with that. When we look at the Schwarzschild solution, right, we state that it has how many Killing vectors? That seems supposed to know. Four Killing vectors, right? 1 was conservation of time, right? 3 momentum, energy. So it's time independent, right? The Schwarzschild solution. It's static. But here, I somehow broke that. I mean, I saw that particles can get in, but they cannot get out. Why is that? Somehow I broke this symmetry. Where did I do that?
What? Why is it a break of symmetry?
What?
Why is it a break of
Because time is working only in one direction. I can go in one. What?
You can change coordinates.
Right. Change a coordinate. That's right.
Maybe because we only changed one.
Right. I didn't have to change it to U tilde. That was my choice. That's where I broke it. I could have as well changed it to V tilde. My selection. What happens if I change it to V tilde? So rather than T goes to U tilde, let's do T goes to V tilde. What's going to happen? So in that case,
The outgoing velocity is going to be 0 and the incoming.
exactly. So if I write down again the null radial delta-z, right, so ds squared, PL minus 1 minus 2 gm over r, and v tilde squared. Now, instead of a plus, I'll have here a minus. Minus dv tilde dr plus dr dv tilde plus r squared d omega squared. So now if I draw the same plot, but for v tilde,
Is V tilde tyrant?
yes,
The minus.
will be.
Because of the minus.
Because of the minus here. Minus here. I'll say it right away.
But it's up.
And again, this is r equal to gm over c squared. What are we going to get now? Yeah, mirror image, right? So now I've got no problem getting out. Just a second. Now once I reach this radius, I can only get out.
The other way
Oh, the
around.
other one.
Excuse me. Yeah. Oops. What I really did here, right? I basically extended space, right? We said, and you said rightfully, I mean, something looks very strange here, right? Because to get here, my problem was that t went to infinity here. So it went to plus infinity, and I did this mathematical manipulation to overcome that, right? So getting here would mean that t goes to minus infinity. Really, so that was like, that would be in the infinite future. This will be in the infinite past, really. So what?
Looks like a white ball.
Right, sort of, right? So this will be t goes to minus infinity. Okay, confusing. So we need to play a little bit more to see the full picture, which is going to be even more confusing. Questions? Yeah.
You said that d, v, and du are time-like because of the minus sign.
Correct.
This makes sense only if the metric is diagonal. No?
No. You can, the metric is, I got no problem with the metric here. It's not diagonal, but it's a very well behaved.
No, I don't have a problem with the metric. Just that to call the coordinates time-like because the coefficient only on the diagonal of the
It's not only the diagonal. You can do.
יש לו עוד רכיבים.
Yeah, I mean you can how to say, you can find the principal axis of the matrix.
הייתי אומר את זה לפי ערכים עצמיים, לא לפי
You can do it, but this is the standard way you should see textbooks. That's what I'm saying.
How can u tilde be the future and v tilde also be the future?
Both of them are t. I just added and subtracted this Tortois coordinate r star. So both of them would be going with
Advancing with t.
You can't just advance with t.
When
Because, as you've seen, you can't just stay in place. When you're advancing, the r star also changes.
yeah, that's what I get. Look, guys, you have to think of that, and when you think a lot, you'll still be confused. So that's okay. That's just confusing.
That's the way you go.
Let me proceed on and see where we get.
Couldn't we increase in u, decrease in t, but increase in r stuff? So
No, because they're all connected to each other. Right? R star is defined as a function of r. Right? Remember how we defined it. Okay. So we have to do a little bit more work. Erase that. Okay. So we need to continue doing some mathematical manipulations. So rather than u tilde and v tilde, thank you. Yeah, r star is just a function of r, so it doesn't really matter. Right. I'm going to write down even newer coordinates, so u prime and v prime, which is e to the power u tilde over 4gm. And this is e to the power minus v tilde over 4gm. If I want to express them in the original t and r coordinates, this is going to be equal to r over 2gm minus 1 to the power 1/2
Absolute value.
e to the power, sorry?
Absolute value.
What?
Not absolute value.
No. E to the power r plus t.
Because when you're inside the structures where
Yeah, there is, look, that's the issue. If I'm just using the t and r, I'm not going to really get inside the Schwarzschild rings. That's why this is the correct definition in a way, because it's general. And when I do that, I am sort of limited. In principle, if I just plug in these values, that's what I'm going to get. So this is going to be r over 2 gm minus 1. Hold on. R1 half e to the power r minus d over 4 gm. And then if I write the metric, the correct way of thinking of that, you should not be too worried about whether this is how you write it in terms of r and t. The thing is whether this is a valid solution to the Schwarzschild metric. Right? That is the true, the only thing that you worry. If there's a solution, then you can use this solution point. That's all. So in terms of these new coordinates, then I can write down the Schwarzschild metric, ds squared as a minus 16 g cube m cube over r e minus r over 2 gm du prime dv prime plus dv prime du prime plus r squared d omega squared. Okay. So now you see that there is nothing really happens at this Schwarzschild represent at 2 gm. The metric is well behaved regardless of that. We can use so basically we can use now u prime, v prime, theta and phi. R is now a function of u prime and v prime. We can do that, but we don't want to do that because we still want to do a time-like vector and 3 space-like vectors. And both of these are null vectors, as you can easily check. So we're going to define, yet again, rechange the definition and write u. I'm using sort of an old, this is in some textbooks, and in Wikipedia this appears as an R. Capital R. U is 1/2 u prime minus v prime. So this is equal to r over 2 gm minus 1 to the power 1/2 e to the power r over 4 gm cosine hyperbolicus of t over 4 gm. And v, which is also capital T, remind you it's 1/2 u prime plus v prime. So this is equal to r over 2 gm minus 1 to the power 1/2 e to the power r over 4 gm, and then sine hyperbolicus t over 4 gm. And in terms of these new coordinates, these coordinates have a name, which you may have heard of. These are called Kruskal coordinates, or other name is Kruskal-Sekers coordinates. So t, r, theta, and phi, these are called Kruskal-Sekers coordinates. And in terms of them, we have that ds squared is equal to 32 g cube m cube over r e minus r over 2 gm minus dv squared plus du squared plus r squared d omega squared, where r is really a function of u and v, or of capital R, capital T, and is defined by the relation u squared minus v squared is r over 2 gm minus 1 e to the power r over 2 gm. So you really need to solve this complicated function once you give an u and v, that you can find what is the true radius r. So here it's quite clear, right? The metric is very well behaved. V is a time-like coordinate. It has a minus, so that's why it's called capital T. What I'm using is sort of in older textbooks, you'll find this U and V notation. In some newer textbooks, you'll find this T and R, and in Wikipedia, I just checked this morning, it's also they use a T and R, so that's why I put it here, in case you look at Wikipedia.
Isn't R confusing with the Ricci scale?
What?
Isn't R confusing with the Ricci scale?
I don't like to use that. I mean, the classical notation that you'll find in some older textbooks will be always the U and V, but I mention it to you because that's what you're going to see. And you're right, R is typically reserved for the Ricci scale. So okay, so metric is well behaved. There's no problem, nowhere. Right? V and U are well defined. V is a time-like, U is a space-like. What is dv over du? dv du? Plus minus 1. It's very clear. Everywhere the light can go 45 degrees. No problem. What? What?
Why is dv over u?
They both have the same coefficients, right?
Okay.
Multiplying both of them by the same.
Oh, but when you're going in a non-geodesic and going radial direction.
Yeah, non-geodesic. This is 0, this is 0.
Yeah. Non-geodesic in the radial direction.
Non-geodesic in the radial direction, yes. dv over. I'm only talking about non-geodesic in radial directions here.
What happens when you, I think, non-geodesic?
And you go in circles, right? Non-geodesic, you go anywhere you want. Right?
Yeah, non-radial direction.
Non-radial direction. You have some you're complicating your life, but you can do that. But, okay, so null radial geodesic. Right, so ds squared is equal to 0, d omega is equal to 0, d omega squared. So we have that V is a plus minus U plus constant. What is R equal to GM? So Schwarzschild radius. What?
U equal
Plus minus.
yeah.
Right. U equal plus minus. Let's draw that actually. Right. Can you see it right here? It's not- This is U. This is V. Right. U equal to plus minus V. 45 degrees. Red wire. Right, U is equal to plus V, U is equal minus V, this is R equal to GM. So R is equal to GM. Yeah.
When R goes to infinity, and R, capital R and capital T or U and V are not converging into RT.
No, they're different coordinates.
Wait.
Yeah.
In this form, the metric is radio. Oh, it's not states. In this form, the metric is diagonal.
Okay.
But we had this derivation of the structured metric in forms of requirements. They're expressed in this form. We won't get this form from the derivation before because R is a function of both U and V.
Now I'm thinking of R as a function of both U and V. But actually I did get this metric from the derivation before. I started from the Schwarzschild metric written in RT and then I just manipulated it. Now of course I didn't have to. I could just write the Schwarzschild metric directly in this form. Or if you want, I can just take that, plug it into Einstein's equation, and you see this is a solution to Einstein's equation. Which is essentially what I wanted, right? That's the whole point. What is a constant time? Constant t. Constant t. So I just have to divide those, right? So if I just divide those, then V over U is a tangent hyperbolicus of t over 4gm. So when V over U is 1, what does it mean about the time? Still? I guess it's infinity. Infinity. Right, so t is equal to infinity. We're talking about this surface here. Now, we don't have the r equal to 0, right? So when r equal to 0, so basically you can have that u is go to plus minus infinity. What about r goes to 0? R equal to 0. What are we going to have? It means that v squared needs to be smaller than u squared plus 1. Right? So this would look something like that. This is excluded. The space. What? When v squared is equal to u squared plus 1, right, then r is equal to 0, exactly. Right, you cannot have r which is smaller than 0. That's why we have this restriction. This is a restricted, this doesn't exist, and this is r equal to 0.
So what happens if you start with a point and then you go and
Wait. So, one step at a time. Yeah?
You're cheating a bit because you said the coordinates aren't well defined inside the source earlier.
No, these coordinates are well defined.
Just to start, we have a square root of a negative number
Why?
in
Where do you
defining u and v.
No. Again, okay. The only cheating, because it's not a real cheating that I was doing, is that I derived that from the R and T. But again, what you should think of is that what you really care about is that this is a solution to Einstein's equation. Now you can take this solution, plug it into Einstein's equation, and you get the solution. It's the same solution.
So I think the problem is that when r equal to 0 and you plug it into this definition, you get minus 1 to the
No, just get that u squared minus v squared is equal to minus 1.
But you derive it from this equation. If you plug it to this equation,
That is true. That if I try to play too much in here, then I'll run into mathematical problems. I agree with that.
So
That's why it's you have to be a little bit careful in how you do it, in the way you interpret that. But I don't need to do that. Okay, I can simply do that directly instead of deriving Schwarzschild solution in R and T as we did. We could derive it like that. I don't know if they derive it directly like that or they just check it afterwards, but you can easily check that. Right? So this is a valid solution. It's just more complete solution. Wait. Again, what you're saying is a mathematical malfunction in the derivation when r is smaller than Schwarzschild. But this is again, it's not valid because then time is more than infinity. So that's where you get stuck, right? Because the time goes to infinity at Schwarzschild. So it's really an illusion of the way you are. If you try to do the full derivative from the Schwarzschild in RT coordinates. Now,
Question.
just a second. Just let me finish one thing. So constant time is, if time is constant, then P over U has some value. So constant time, we look to something like that. Just constant. Use that one. Constant time will look something like that. These are equal to constants.
What is straight lines?
Straight lines. Right? I put some time here. V over U is constant. Therefore, so this is t equal to constant.
So what's the time at
What?
u equals v equals 0?
What?
What's the time at the point u?
Wait. That's all. Constant r. If r is constant, that means that u squared minus v squared is equal to some constant. The constant r would look something like that. This is r equal to constant. And we said if we are anywhere located anywhere in that space, right? The v du is a plus minus 1. So anywhere we're here, there is space, right? Our light cone would look like that, always. Regardless of where we are.
T is not defined.
Fine, but v and u are defined. Again, the thing that confuses you, many of you, or some of you, know, right, is that I did this derivation I started from T and R and I did some mathematical manipulations, and on the way you say, okay, there are regions which are forbidden. Because there are regions where T is greater than infinity, so how can you do that? When you do this manipulation, you should get something which is unphysical. But no, because this is well defined by itself. And I can just take that and I translate that into T and R using that equation and that equation. So I can start from U and V, which is perfectly defined anywhere, and I can move from that to T and R, which is the coordinates that I'm used to thinking. Then everything makes sense. Everything is regular anywhere. Now I can. There are 4 regions here, right? So this is region 1. This is region 2. And how did I mark it? This is region 3. This is region 4. Where are we?
2.
No. Where are we?
1 and 4.
No, 1. We're in region
Why?
1.
What's
Oh, wait. We are here. We're somewhere here.
Why is that?
What?
Why is that?
We are outside. I mean, what is this green lines represent? What do they represent?
event horizon?
The event horizon, right? We are outside of the event horizon.
But if you just add one coordinate, make it, this is a one-dimensional world. If you just make it a two-dimensional world, that this
It's already two-dimensional in TNR.
Yeah. So make it a three-dimensional world. That will be a cone, and 1 and 4 are connected.
No. You'll have another. No, they're not. That's the thing. They're not connected.
It's not a cone of. Okay.
There are some things you really have to digest. You have to think of these things at home. We are region 1. We're here. We can move anywhere we want. There's no problem. Right?
Except to 4.
Yes. This is going here is no. We are always going. Forward in time. It's always like that. And this is constant in time. Right? This is a constant time. Forward in time. We have to always go on. Now we can cross this region. There's nothing that prevents us from crossing it in these coordinate systems, you can see. What is region 2? It's inside the black hole. What is this region here? This is the singularity. Now you can easily see, once you cross into the black hole, all future directions will take you to the singularity. You will reach there. And you cannot cross back. It's 45 degrees, and this is 45 degrees. You cannot cross back. And of course, the less you do, the longer you live until you reach a singularity. What is region 3?
Something trying to get out.
So this is the white holes. This is what we said if we just switch the coordinates from U tilde to V tilde. These are the white holes. Right? Now,
So if you put a light cone here, you cannot enter it.
yeah, if I have a light cone here.
No, on the border.
Never, doesn't matter. You only get out. No, I'm not worried about this. I'm saying that this is not a real. Why do I say it's not a real?
But we need to
Because
measure
that's it.
Because
Because that
No, there's no causality. No problem with causality. It's all taken care of. Why do I say it's not real? Because what is this line representing? This is time. What is the time? Time here is plus infinity. What's the time here? Minus infinity, right? So, for something to get out of here, mathematically it could have, but this would have been a time which are minus infinity. Now, what happened at time minus infinity? Well, now comes the physics, right? Remember, universe was small and dense, and remember that when we derived this Schwarzschild solution, we derived it for an empty universe except for one point source. So that means that this Schwarzschild solution was not relevant sometimes in the past. So that's why I'm not worried.
But this is not a minus infinity.
It is a minus.
So,
Same way as this is plus infinity.
So you cannot get into the black hole.
I can get into the black hole. I cannot see that I'm getting into the black hole.
Okay, so you can see you're coming out of a white hole, but you can't get out of a white hole.
Well, for a particle, let's say that there was a particle that could get out of the white hole. This is true. But for me, it will take an infinite amount of time.
Okay.
So I will never see this particle reaching me.
But the cone still exists.
Again, yes, but time minus infinity, the metric was not, the universe or whatever there was there could not have been described by the Schwarzschild solution. Right? So this solution was not valid, really. So that's why physically I'm not concerned. Which leaves us to region 4. With region 4. What is this region 4?
another universe.
Yes. This is a universe which is a mirror to our universe. We don't have any way of getting there. As opposed to what you say, it's not a closing like that. We're adding a theta and phi. It will be a different dimensions here. The only way to reach this universe is basically to cross here, right? The constant time and get here. So this is essentially what's called the wormholes that will take you from one universe to another universe. So again, mathematically, it is a valid solution. Yeah, we don't have any way of knowing anything, but if you see science fiction movies, that's what they mean. To get there, we need to be able to travel faster than the speed of light, so we can reach a black hole and get out. This is a mirror image of our universe.
How do we know we live in 1 and not in 4?
Why do you care?
I don't know. They said we live in 1.
Okay, so you could say we can switch that. We live in 4 and then the mirror will be 1. Okay? Cool, isn't it?
Wait, but
Okay.
in world 4, you can.
It's a valid solution.
No, but you can only get into the.
No, it behaves exactly the same as our universe.
No, but you can. But now,
Yeah,
now
exactly
the
the same as
region,
our universe.
now the edge of the white hole is at infinity, and
No, it's
and the edge of the black hole is at minus infinity.
no, because your future directions will still take you, or you may reverse that. So it will be a black hole for you and white hole.
So this is the equal to infinity, and this is the equal to minus.
I didn't think of that, but I think yes, that this will be this to plus infinity, which means that your future direction will take you here. So everything is reversed. That's why it's a mirror image.
So you can only get into the white hole.
Yes. What we call a white hole, but for you it will be a black hole.
Ah.
So that's why it's sort of a mirror. Right? So this is future directions will be taking you here. Well, here in the future direction will take you here.
So where are the additional dimensions other than the radial ones?
I did not plot them because I just did a non-radial. If you want another one, then you have to do other dimensions. You know, this is a 2-dimensional part. I don't have a way of 3 dimensions. I can try to draw 3D here. 4 dimensions I can. Cool. Okay, so just final few words. You asked me a little bit about that, which I was a bit surprised that you asked. Where do we see black holes in nature? So first, we do see black holes in nature. We know that exist for many years, not just because theoretically were predicted, but because we have ways of measuring them. First, indirectly for many years, and in recent years also directly. Of course, what do we mean directly? We don't see the black hole, but we see the image that surrounds the black hole, and we can infer many of the properties of the black hole. How are black holes formed in nature?
Collapsing.
Right. So what happens to our sun? How is our sun working? Yeah, burns is a bit of a it's not exactly the word. When we say it fuses, right? Say burning, normally it means that you have a chemical reaction of oxygen with something that produces another chemical, right? So in the sun, it's a burning of hydrogen. Just say burning, right? It's a hydrogen which is being fused into helium, and then what happens? What forces act on the sun? The stellar interior.
The gravitational.
Right. So on the one hand, you have gravitation that tries to
thermal
push it in, and then you have pressure. Right. You have thermal pressure. Essentially, it's radiation pressure, and it's very easy to show that this is a very stable situation. That's why our sun is a very, very stable. It's not changing its size. It's not changing its luminosity. It's extremely stable, which is very good. Otherwise, life would not have evolved. Or anyway. And that's gonna last. Do you know how long this lasts already? 4.5 billion years. And how long it's going to last? More?
A few hundred years.
Yeah, so another 4 and something billion years. So you don't need to worry. The sun is not going to change while we're alive. We're not going to children or grandchildren, and everybody will ever know us alive. The sun will still be the same sun. Until what? Until what happens? Until it runs out of you. When the hydrogen,
Not enough.
yeah, when it runs out of hydrogen, right? What happens when it will run out of hydrogen?
Fusion stuff.
Actually, it will continue, but with heavier elements. So essentially, it will consume these as well.
Will it be heavy enough to fusion helium?
No, the sun is.
The sun.
Yes, of course. So if you look at the mass, it's the units of solar masses and then radius. Okay, so I can also do that. Have in mind. So our sun is somewhere here, right? Now what will happen? What happens when the fuel runs? What? It collapses, right? And until when it collapses? I mean, nothing will be able to balance gravity. It will just to collapse. Until when? Which pressure?
The
No, gravitational pressure.
the
The generosity pressure of what? Electrons, right? Electrons are fermions, right? So if you try to squeeze them in together, right, they object, right? You cannot put two fermions in the same state at the same place, right? So that's called the generosity pressure, and then it will stay like that. How do we call such stars? Wide ones, right? So and the limit of the masses for that?
1.4.
Yeah, that's called the Chandrasekhar limit. So it's a 1.4. It's called the Chandrasekhar limit. It collapses to a white dwarf. For our sun, that's what's going to happen. It will end up its life as a white dwarf, which will slightly decay over billions of years, getting dimmer and dimmer. What happens to stars that are heavier than our sun? More than 1.4 times heavier than our sun?
They push the electrons into the protons.
Right. The electrons will merge with protons and becomes neutrons. This is called neutron star. It's not made fully of neutrons. We don't know exactly how many neutrons inside. Likely 80 to 90% of the stars are made of neutrons. The rest are other ingredients there. That's called a neutron stars. This is a white dwarf. And then it will be like a neutron star. We're not sure what is the upper limit because we don't know what is the equation of state of neutron stars exactly. What? It's about, but we don't know, and there are many things. I mean, at these stages of collapse, things are very messy because there's a lot of wind ejected, so we're not sure exactly what we'll end up with.
Is a neutron star active? Is there
Yes,
anything happening there?
yes. They have strong magnetic fields. What we call pulsars are actually fastly rotating neutron stars. Angular momentum is conserved, so now it's smaller, so it will rotate faster. And also magnetic flux is conserved, and could be also magnetic fields are generated inside, because it can become a giant superconductor. And I'm not sure exactly under what conditions, because I'm not an expert in that. But then what we do end up with is huge beacons, really, of magnetic field, which we see now as they rotate. And there are charged particles, and they are emitting emission from radio to X-rays.
So it's losing energy. I mean, it's
Yes, it is losing energy, but
it may
it
also
will take about the age of the universe
It's
to lose all its energy.
energy.
Of course, I mean, if it's rotating and it's pulsating, it must lose energy.
Everything can only lose energy. You can only.
Yes and no, because you can accrete material inside, and then if there's gas accreting, then you can gain more energy.
Everything can either lose energy or
Or accrete more energy,
Or
accrete more mass. Yeah, that's called neutron stars, and we see them as pulsars mainly. Neutron stars that we see.
If it loses enough energy, what will it decay to?
What?
If it loses enough energy, what will it decay to? You just say
Nothing. It's just a neutron star, which is boring.
It's just slower.
Slow down. Slow down. But the time it takes to lose energy is comparable to the the age of the universe. There's no need to worry about that too much.
Wait for too long.
What?
Just wait for long.
If you have time, yes. It's likely. Actually, pulsars are extremely. I'm sure you know that, right? Pulsars are extremely accurate beacons. So the rotation period is extremely accurate. So it goes to good to 10 orders of magnitude after the decimal. 10 points after the decimal point, you can measure exactly how the periodicity changes. And if you know a little bit of the history of this field, I think it was 1975, Pulse and Taylor, they were the first to show evidence for gravitational waves by comparing the decay time of pulsars. This was indirect evidence, 40 years before gravitational waves were actually measured. So this is, and that was a Nobel Prize, I think, 1975 or something, or 75 was the discovery. Nobel Prize was a few years later. So then you got the neutron star, let's say approximately 2. What happens if the initial star is heavier than that?
collapse again.
Then it collapses again. There's nothing that will stop it, and then it will end up as a right? So from here on, it will be a black hole. That's it. That's as far as we understand. Now, more on that is in the course of physics. There, 1, 2, I don't know. Questions about it? What? Yes.
What happens to all this nice drawing if I want to draw a world with 2 black holes? I mean, what will happen? Is there anything new that we find out? What happened? Oh, T infinity and all that.
If you have to, first of all, the metric, the problem is to find the metric. I mean, as far as that, if you look at this shape, it's not going to be an accurate description. This is an accurate description of a metric of a single non-rotating black hole. If you go for, if you want to do the full metric of 2 black holes which are nearby each other,
okay,
then you cannot use this metric. You need now. Today there are of course solutions to that, but as far as I know, they're all numerical solutions.
Okay.
Because I don't think you have. There is a way of having.
Is there a picture of coordinates that someone can present?
Not that I know of. What you're seeing is pictures of black hole that you're seeing is the standard picture that you're seeing that I showed you, sort of the cartoonist of like coordinates that fall in, and that, but just 2 of those. But there's nothing really in it. Again, guys, this is supposed to make you think. This is a basic course in general relativity. Now you can go on. I give you the conceptual things here. Now, if you want to go to various details of how to, there's nothing that is conceptually different if you do it in 2 methods. Okay? It's way more complicated, of course. It could be quite interesting, could be quite useful when you do calculations of binary mergers, how much energy is extracted, what are the gravitational wave signals that we're seeing, expecting to measure, etc. And it's going to be quite useful, but it's not conceptually different than what we learned here. Right? That's why I told them, we can go on if we have time to talk about rotating black holes or charged black holes. But it's not. It's going to be a way more complicated metric than the Schwarzschild metric. It will take some time. There are some interesting things. There are especially things called ergosphere, things that we don't touch. But they don't exist in Schwarzschild. But once you understand the basic concepts of how these things work, like finding a solution to Einstein's equation, then for me it's more technical detail of how to do it. These little conceptual new things. Okay? That's what I see. Now let's go on. If you don't have any further questions about this subject, then I want to move on to the last subject of the semester, which is cosmology. I say last, but if we have time, which I don't think, I may have time to have like 1 lecture about gravitational waves, so I give you some sketch of how these things work in gravitational waves. I don't know. Again, I don't view it as something which is crucial, because if you understand everything we're saying here, taking a book and reading about gravitational waves should be quite straightforward. So let's talk now about cosmology, or start the discussion of cosmology. Unless you have any last questions about black holes. Cosmology. What is cosmology?
Study of the universe as an object.
Not as an object, but I would say studying the global properties of the universe. We can study objects, stars, galaxies, black holes, exploding stars, whatever. Or study the global structure of the universe. starting point is what's called the cosmological principle. Like this course because of many principles in this course. So cosmological principle is the modern description of what's known as the Copernican principle. What is the Copernican principle?
The Earth is not the center of the universe.
What?
The Earth is not the center of the universe.
Exactly, right. So Copernicus was the first guy. Copernicus was the first to say that we are not, and until Copernicus's time, people were sure that we are at the center of the universe. Some people still think so. If their age is more than 5, they may have a problem. Until the age of 5, I think it's still okay. So Copernican principle, right? Copernicus said we are not at the center of the universe. We are not at the center of the universe. Right? To be more precise, what Copernicus really said is that we are orbiting the sun rather than the sun orbiting us. Sun, moon, everything else, right? The cosmological principle states that the universe is what?
There is no center.
Yes, really. What it says is that the universe is homogeneous and isotropic. Universe is homogeneous, and isotropic.
Homogeneous in this context means.
What?
Homogeneous in this context means.
Sorry?
In this context, homogeneous, what does it mean?
Okay, what is homogeneous?
Looks exactly the same.
Right. Looks everywhere, it's the same. So what is isotropic?
It looks in every direction.
It's the same in every direction that we look. Right? Isotropic means everywhere we go, it looks the same.
No, this is homogeneous.
Sorry, this is homogeneous. Homogeneous is that doesn't matter which point I am on the universe, it all looks the same.
But this means.
Isotropic means I'm in one point, I'm looking in all directions, and they all look the same to me.
Function which is both homogeneous and isotropic is constant.
What?
But the function which is both homogeneous and isotropic is constant.
So pretty much. So obviously, it's a bullshit. Right? If I look to the left, if I look to the right, I don't see the same thing. Right? And if I'm here in this classroom, and if I'm going to the center of the sun, the physical conditions are not the same. Right? So this is not true. But
On the larger scale.
right, on a larger scale. On what scale? We know that we have a solar system, that's not enough. We have our galaxy, which is not enough. We will have clusters of galaxies, still not enough. If you go to larger scales, then it is likely correct. How do we know? So there are several ways that we know. Right, so first thing, there are galaxy surveys, right? We're making surveys of telescopes that look in different directions in the universe, and we're looking at galaxies, and they all look the same in different directions. Second is we're looking at photons, right? There is diffusive, what's called X-ray and gamma ray light, and it looks the same. And most importantly, something which I think that you should say, you should know. It's called the CMB, Cosmic Microwave Background. CMB. It's called the Cosmic Microwave Background. That's called the 2.7 degrees Kelvin radiation.
We calculated.
What?
I think we calculated in the homework.
Did you?
Yeah, we have pion, photon, max pions.
That can be done. You didn't calculate that.
Yeah.
You might use that. What?
It was given, the temperature was given.
Temperature was given. I didn't ask you to calculate it. What?
So not energy.
You can calculate this energy, right? But this is something which was discovered in the 1960s. It was predicted, right? Okay, so if you go outside of Earth, like an astronaut, actually you don't need to go outside. I mean, you don't remember that. You may remember that because you look a little bit older than the most of them. It used to be like these televisions that you had to tune them.
Yeah.
And there was a noise, right? It was always
Shelling.
what? Shelling, yeah, shelling, right?
Snow.
Snow. That was before the days that everything was in cables, right? So there was the snow, right? The snow was right, and there is a noise essentially, right? Now there is a physical limitation. You cannot get rid of that noise entirely, whatever you do, because we're surrounded by this 2.7 degrees Kelvin. It's a thermal origin, very weak, but it's always there, and it's completely homogeneous, regardless of where you look at. Not exactly completely homogeneous. We are moving, so it's little Doppler boosted. But when you correct for our motion, it is homogeneous. Still, there are some fluctuations, but it's a very small fluctuations. It's always there. Okay. It was predicted in the 1940s. Was discovered in the 1960s. So we said 1 CMB, 2 number counts of galaxies of large scale galaxies at larger scale. And 3, we said X and gamma ray background. So we said homogeneous means same everywhere in space. Isotropic, we mean same in all directions. Same everywhere in space. Let's just say it mathematically. If I want to say it mathematically, well, I would say it. So we're going to do the mathematics shortly. Let's use a mathematical way of saying it's the same in everywhere in space. Right. Very good. It means that it's invariant under translations. And isotropic, invariant and rotations. Properties are the same in all directions, which really means invariant and rotations. Invariant, I mean the universe, right? The universe is invariant under rotations.
By the universe, I mean the metric.
I mean the universe as we see. Essentially, yes, it would be the metric.
How would we describe the universe?
Just the same, but by the metric, of course. Now, yes.
But in a very large scale, we're talking about the Earth-like scale. It's the center of mass. כאילו מרכז מסה, כאילו אז תגידו, גם בסקלות מאוד גדולות,
מרכז המסה.
גם בסקלות מאוד מאוד גדולות, אם אני רואה הכל אותו דבר, אז אני מתחיל ללכת ודבר הכל, זה תכון הפוך,
לא? אתה לא מתחיל ללכת, אתה נמצא בנקודה מסוימת. עכשיו אתה עובר לנקודה אחרת. עכשיו אתה מסתכל מבחינה סטטיסטית.
אחר פתאום אני נמצא אבל בחללית שנעה במהירות גבוהה.
לא, אתה לא נע.
מה זה לא נע?
אתה לא נע.
אני לא יודע אם אני במהירות גבוהה, איך אני יכול לדעת?
נכון, אתה אומר שאתה לא יודע, אתה צודק, זה לא משנה. שוב, תחשוב שאתה באמצע הים, אתה נמצא בסירה, נתקעת עכשיו באמצע הים, אתה בסירה, חשוף לגמרי לכוחות של הזרמים, אתה באמצע האוקיינוס השקט. אכלת אותה, עכשיו אתה מסתכל מסביב, אתה לא יודע מה קורה, הכל נראה אותו דבר. אז ככה. אוקיי? To be even more precise, when we say homogeneous, the mathematical definition would be that given 2 points, homogeneity, right? Given 2 points, it's a P and Q on the manifold. Yeah, there is an isometry. That takes P.
So is that a symmetry which should make some conservation?
Of course.
Like energy and momentum?
Of course. We're less interested in that right now. Let's see where I'm heading, just a second. Can you think of a metric that is isotropic but not homogeneous?
Yeah.
Yes. Right, that's right. Correct. Or a cone or something. Yes, correct. A metric that is isotropic but not homogeneous.
So like the solar system.
What? What?
So
Yeah, sorry.
every point is
Yeah. Schwarzschild would be isotropic but not homogeneous. As asked homogeneous but not isotropic.
if you have a two grid of like
What?
אם יש לך כאילו גריד של נקודות שהמרחק הזה הוא A והמרחק הזה הוא B זה לא טוב, אני מספר, אבל
הומוגני, אתה זה לא איסוטרופיק.
לא, זה כן הומוגני, כי זה
No. I thought of a cone, right? If you have something like a cone, but this is the same as a Schwarzschild. Homogeneous and not isotropic would be if you have a flow. If you have a flow of things, then
In one direction.
Yes, in one direction.
A cone isn't equivalent to the Schwarzschild metric.
What?
A cone isn't equivalent to the Schwarzschild metric.
No, this is equivalent. Yeah, but it is.
A cone is flat.
No, of course, but it's not equivalent. But it's the same idea that you can think of something which is isotropic but not homogeneous.
Oh, wait a second. Why flow is not isotropic? Is it?
Just
It's
isotropic.
homogeneous. It's not
It's homogeneous but not isotropic.
because everywhere you are, you still see something
Yes.
moving. But if you look this
Look at
direction,
different
that
direction, you see it's a different. Now, if you have a space that is isotropic everywhere, it is also homogeneous. And also, if it is isotropic around a point and homogeneous, it means it is isotropic everywhere. Okay,
why
that you have to think
explain
of.
this?
Just think of it for a second. When you see it
You need
first.
to assume that in infinity it's
What?
stationary. You have to assume that at infinity it's stationary.
No, you can't assume anything on it. I mean, it's infinite space.
What is it?
Now, hold on. Okay, I'm saying that I get you more confused and more.
What does isotropic mean in terms of manifold?
Isotrope.
Yes, in terms of manifold.
That I have, it's invariant under rotations. Right. Invariant under translations, invariant under rotations. One thing which is kind of related back to the question that you were asking me. Yair, I think your name. Yes. When we look at the universe, at the galaxies, right, we are seeing that on a large scale it's isotropic and homogeneous. But there's one star, Chovit, which is what? The universe is expanding, right? Since
So
Hubble,
it's
we know that the universe is
around.
expanding, right? So when we speak about homogeneous and isotropic, we're talking only about the spatial part of the universe, not about the temporal part. Okay? So observationally, the universe is expanding. Remember that I told you at the beginning that when we have to refer to three vectors, we're going to use Latin indices. That's exactly where the things can get it. Universe is expanding, so it is homogeneous and isotropic. Only in the spatial part. a technical term, which I guess you know. If a space is homogeneous and isotropic, how do we call this space? There's another name. Space that is both homogeneous and isotropic everywhere. Has a name? Right, that's a maximally symmetric space. This is a maximally symmetric space. And this was isotropic. This is equal to maximally symmetric space. Now, because it's homogeneous and isotropic only in the spatial part, technically what we're going to do is we're going to look at the maximally symmetric subspace of the full space, right? The space is four-dimensional, but the spatial part is the maximally symmetric part. And so this is a maximally symmetric subspace of four-dimensional space. So we're going to derive the metric for this maximally symmetric. For four-dimensional space, which has a maximally symmetric three-dimensional subspace. Okay, this has a name. Then the name of the metric is called nearly yes. It's called the Robertson-Walker metric. F is for Friedman, and the difference is that the maximally symmetric subspace we're going to do, we don't need to solve Einstein's equations really. What does it mean in terms of well, mathematically for us, what does it mean maximally symmetric subspace? Maximally symmetric space, forget about the subspace for a second.
Spheres.
What?
Spheres.
Sphere is an example, right? Sphere is a good example of maximally symmetric. It's not the only one. Another one which you have, right, is flat, right? It's also maximally symmetric. Now, mathematically,
The metric is the same.
it's not the same metric. For an Euclidean space and a spherical symmetric space, it's not the same. Think of the two-dimensional. Think of a two-dimensional surface of a sphere and Euclidean space. It's not the same.
No, it's the same all over.
It's the same all over, right? Now, I ask you a question in mathematics, right? When I say a space is maximally symmetric, right? How do I describe mathematically?
You have the most killing vectors.
Have the maximum number of killing vectors. Maximally symmetric space, that means it admits maximal number of killing vectors. And if the space has n dimensions, what will be the maximal number of killing vectors?
N.
What?
N times n plus 1 over 2.
Good. How do you get that? It's n plus n minus 1 times n over 2. It's n plus 1 over 2. What is that? Translations, right? For n-dimensional space, I have n translations. And what is that? And this is n rotations, right? Over 2 because it's the same as rotating one.
You pick two axes and
Exactly. Right, so this is the maximal number of translations. And this is the maximal number of rotations. And this is the maximal number of killing vectors for n-dimensional space. Now, that can be a little bit confusing, right? Because you can immediately see that if the space is equal to 2, you already have more killing vectors than dimensions. How can it be? I mean, at a given point, of course, you can only have n independent killing vectors, but the killing vectors would have coefficients which could change from one point to the other. Actually, you had that in your problem set when you're asked to calculate killing vectors on two-dimensional space. Okay, I think now it's digging into the math of. I have to give you some more. We have to derive a little bit more properties of killing vectors before we derive maximally symmetric spaces, and then look at maximally spaces with maximally symmetric subspaces. I just say Robertson Walker would be the metric, which is not a solution of Einstein's equation. When we plug just a metric that represents a maximally symmetric subspace, and then when we take this solution, plug it into Einstein's equation, but now we cannot ignore the matter term because there is matter in the universe, so it's not going to put a zero. I have to put some T mu nu on the other side, of course homogeneous, so it's the same everywhere. Then we get a solution that's called the Friedman solution. So it's a Friedman-Robertson-Walker universe. Okay, just see you on Thursday and then continue the derivation from there. Or begin the derivation.
Question.
Yes.
You said that we are homogeneous isotropic only in the special
part, yes.
Subspace.
Yes.
And this happens now. Does this also shows us that it will remain, or was like that at every future past
We will
time?
discuss that. The evolution of the universe is one of the subjects at cosmology. I can give you already a hint, right? I mean, this will lead us to what's called the Big Bang. We'll discuss that in the past, and in the future we'll see what happens. Okay. Have a good week, and see you all on Thursday. And again, I don't know about your colleagues if they want to come or not. But, if you see them, then ask them. All right.